So in the last video, I started talking about the metric tensor, and I mostly used the Euclidean metric tensor as the example. In this video, I'm going to look at the Minkowski metric as a specific case of a metric tensor that is not the Euclidean metric. And so I have it written here, and so you will often see the Minkowski metric using this eta symbol. So that's eta spelled E-T-A, the Greek letter eta, with mu nu. And so this is the four-dimensional. So it's four-dimensional because we're using space and time. So this is the four-dimensional rank 2 metric tensor used, or Minkowski metric. And so I put the indices in the lower part here, but it would actually be the same if we put the indices in the upper part. So, so this is a metric where putting it downstairs or upstairs gives you the same thing. And so what we see here, what's different, so in here I put the c squared in explicitly. So usually you will see this with c set equal to 1, and I'll talk about that here in a little bit. But for now, let's look at it with the c squared in the 0, 0 position. So that's the time position there. So this is the Minkowski metric. And so yeah, like I said, these negative signs here are probably the main difference, and you will often see it written this way too. So negative 1, 1, 1, 1 with zeros in all the off diagonal. These are the same thing. You will get the same thing either way. It's just a matter of convention. And so if we use the Minkowski metric to do the dot product of two 4 vectors, so that's what I have going on here. So this is our first 4 vector, this is our second 4 vector. So this one is as a column, this one's as a row vector, which doesn't really change what they look like so much in this instance. So the first thing we do is we multiply through and by the Minkowski metric in this column vector. And so we end up with a column vector that looks like this. So we have c squared t, then minus x, then minus y, then minus z. Then we just go through once again, so t times this c squared t, x times this minus x, and so forth, and we end up with this right here. And so this is oftentimes called the space-time interval, and it's usually denoted as S. And we can think of that S as, I mean, it's the sort of the same thing as a length. So in Euclidean space, where if we had, say, y equals, x1 squared plus x2 squared plus x3 squared. So in 3-dimensional Euclidean space, we'd have that, where this instead we have s equals, and then we could have the c squared t squared minus x squared minus y squared minus z squared, and then the square root of that. And so this would be a length in Minkowski space. This would be a length in Euclidean space. And so yeah, that's what I meant in the last video by how the metric gives a coordinate displacement a length meaning, and I'll talk about that a little bit here, or a little bit more here in a bit. All right, so if we set c equal to 1, then this first position here just becomes a positive 1, and our distance would look like this. And so over here I just talked a little bit about how you would go about setting c equal to 1. And so I said we define a unit of distance, and I called it an oh boy it's so big. Uh, and so we could have it be maybe equal to 2.4 times 10 to the 6 meters, or we could have it be equal to 3.0 times 10 to the 8 meters. Then we define a unit of time, and I called it an oh boy, it's so fast. And so we could maybe define it, if we're using this one here, we could define it as 8.0 times 10 to the negative 3 seconds. If we're using this one right here, then we would define it as just 1 second. Then we can use both of those to define a new unit, which I'm calling a mighty lighty. And so our C is equal to our D up here over our T up here, so one of our two T's. So here we have the 2.4 times 10 to the 6 over 8.0 times 10 to the negative 3. That gives us 3 times 10 to the 8 meters per second, which is the speed of light. But one of these, so 3.0 times 10 to the 8 meters per second is one mighty lighty. And so if we're doing the calculations, we would use these new units we defined up here. So all distances would be in an oh boy it's so big, and all time would be in an oh boy it's so fast. Or if we use this second example I used up here, we could define all distances. So each oh boy it's so big as this many meters, and each oh boy it's so fast as this many seconds. And then we would have this one of these as our one mighty lighty. And so anyway, that's just kind of, if you've ever wondered how you end up setting C equal to 1, that is how you would do it. And so here I have the two-dimensional Euclidean metric and the two-dimensional Minkowski metric, which I'm going to be using here in a little bit. And so here I just went over a little bit of index lowering and raising, which I'm going to go into in a lot more detail in the next video. But mostly what I wanted to show is if we have a metric here, which we can set equal to our Minkowski metric, our eta, ij, and with the downstairs indices, and then eta kj with the upstairs indices, we will sum over the j's. So eta 1j and eta 1j would be eta 1 1 times eta 1 1 plus eta 1 2 times eta 1 2. So that's 1 times 1 plus 0 times 0, so that's 1. And then if we just go through all these sums, we get 1, we get 0, we get 0, and we get 1. And so that means that if we have eta with a downstairs and an upstairs index, so it doesn't really matter which order you put the indices in, you end up just getting the Kronecker delta, which just means that it's equal to 1 when I equals k, and it's equal to 0 when I is not equal to k. So the Minkowski metric with one downstairs and one upstairs index is just the Kronecker delta. But it is the case, and I said before, that if you have, so that eta, I can maybe draw it a little better, eta with upstairs is just equal to eta with downstairs indices, whereas the eta, if you have a downstairs and an upstairs index, then it is just the Kronecker delta, so nu and mu. So yeah, that's just a little bit of this sort of index gymnastics for the Minkowski metric. And so now for the sort of physical interpretation of the Minkowski metric. So I have on the right here, this is a Euclidean space. On the left is a Minkowski space. And so in Euclidean space, if you are at the origin and you move in any direction. If you do a coordinate displacement in any direction, so it could be that direction, or it could be that direction, it could be that direction. If you do a coordinate displacement of 1 in any direction, you move a length of 1. Whereas in Minkowski space, if you are right here at the origin, say you move over here, so a coordinate displacement from the origin to this point here, or you do a coordinate displacement from the origin to this place over here, or a coordinate displacement from the origin all the way up to this place right here. So those coordinate displacements, you look at it and you think, well, those are all different coordinate displacements. This place is definitely further away from the origin than this place, which is further away from the origin than this place. But those all equal a length of 1. Remember, I said that the metric gives meaning to a length. And so anywhere on one of these lines, one of these curved lines here, anywhere you go on one of those lines, that is a length of 1. So they are different coordinate displacements, but the Minkowski metric gives them the meaning of being a length of 1. And it'd be the same. It'd be the same if you went to one of the places on that line there, but that those are in the space-like, where these are in the time-like. That goes to the speed of light being the same, and that you can't go faster than the speed of light. These dotted lines are the speed of light. And so you can see, if you were at the origin and you started going the speed of light, you would never actually get to one of these two lines. And so that is why, if you were moving at the speed of light, time essentially freezes for you, because you would never get to a length in space-time of 1. You would never get to that point. And so that is why you have time dilation, because say you went from here all the way to some place up here on it. So that's, a lot of time passing, but it is not a lot of what's called proper time passing. And so actually, if we go back up here, so this s squared, well, I'll actually use this one here. The s squared is the space-time interval, but it is also the proper time, which is using the tau, like this. And these things are equal because we have set c equal to 1. And so what that means is that any interval in this Minkowski space, so this interval, for instance, so the proper time is the same in each of these. And so here I went through just a little bit of calculation. So this is the space-time interval in 2 dimensions. So we just have the time and then 1 dimension. Then over here I have the same. So we see we have x squared and y squared, but this has a plus, where over here we have a minus. And so if we have s squared equal to 1 squared minus 0 squared, so that would just be staying at the origin and going straight up to this point right here. So we see that s equals plus or minus 1. We use the positive version because we're taking the square root. It can be plus or minus, but we're using the positive one, so s equals 1. So if we have s squared equals 0 squared minus 1 squared, then s squared is equal to minus or plus 1. So I just flip this plus or minus, and so we'd put a minus sign in front of it, and we use the s equals 1. And that would be like going from the origin over to this point here. So we have 0 for our time and then 1 for our x. And so if we have a space-time interval of 1 and we have we have 2 on our time. We solve for x, and what we find is that x is equal to the square root of 3. And so that makes sense because so our space-time interval is 1, so that would be anywhere on this curved line here. And so if we go 2 in time, so we would go up to here in time, and then we would want to move over to where we hit that line right here, which would be right here. And if we then go down, to where that hits the x-axis, it hits somewhere right here, just a little bit above. Well, this is 1, so it's a little bit above 1.5. And so that's exactly what we get here. So we solve for x and we get 1.732, which is just, this 2 squared, which is 4, minus 1 squared, which is 1. That gives us our square root of 3, which gives us 1.732, which puts us right here on our on this curved line here. And then, of course, if we look at it in Euclidean space, so p squared equals 1 squared plus 0 squared, well, p will equal 1. 0 squared plus 1 squared, p will equal 1. But then if we try putting a 2 here in our x and then solve for y, what we end up getting is the square root of 1 minus 4, which is the square root of minus 3, which is essentially 3 times the square root, or the square root of 3 times I, which is this. So that's imaginary, which means that it doesn't make any physical sense. And I mean, that makes sense in a sense, because we can't have something here larger than what our total interval is, because we are adding and not subtracting. And so if p squared is equal to 1, then x has to be less than or equal to 1, and y has to be less than or equal to 1. And if x or y is equal to 1, then y or x has to be equal to 0. Whereas over here, if our space-time interval s squared is equal to 1, and t equals 1, then x has to be equal to 0, because that would just be going up to, I'll change color just since I'm already making a mess on here. That would be like going up to there. So x is equal to 0 and t is equal to 1. But if t is greater than 1, then x has to be greater than 0, because this right here is t equal 1. We see that t gets larger as we go in either direction here. So our just t, not the time, not the proper time, and so x has to grow in either direction, and so x would have to be greater than 0. Which makes sense because we're subtracting. So if t goes higher than s, then we have to remove something from t, which is our x, in order to get it equal to s. And that's where that time dilation comes in, because our t will keep getting bigger as we move, where if x goes greater than 0, then our t will have to get bigger than 1. And you can see how that results in time dilation, where if you go from the origin up to some point here, that is a larger t right there. The space-time interval, so the tau would be the same, but the t is actually bigger. And so if you are here at the origin and you just stay standing still and somebody else starts moving up to here, so that would be a t right here. And so to you, that is a longer time than it was for them. And so that is where that time dilation comes from. And you can see how that sort of falls right out of this Minkowski metric. But anyway, the sort of main takeaway as far as just straight up learning about metrics is just that the metric is what gives a coordinate displacement a length meaning. And so the length in Minkowski space, where we have the Minkowski metric, is different than what length is in Euclidean space. And so that is kind of the main takeaway here, is that uh, when we want to talk about length in our space, we need a certain metric, and that metric will tell us what length means in our space. So, like I said, there's a difference between a coordinate displacement, which would be, say, moving from the origin, and I'll even change the color again here, moving from the origin to anywhere on this line up here, where a coordinate displacement here is moving from the origin to anywhere on this circle. And we can see that a coordinate displacement is just equal to the length in Euclidean space. I mean, that's what Euclidean space is, where a coordinate displacement is essentially equal to the length. And well, in orthonormal basis anyway. But anyway, so a coordinate displacement in Minkowski space is, you can have different coordinate displacements, but they're all equal to a length of 1. And anyway, that's the take-home message for this video. I don't want to keep harping on it too long. I hope you found this video helpful, and I will see you in the next video.